Welcome to the neuron, or nerve cell. Neurons communicate using an electric signal termed an action potential, and today we're going to take a look at how action potentials are generated and propagated. Stick around and we'll talk about what happens in myelinated axons as well. Let's take a look at our cell. The blue area at the top of the screen is the exterior of the neuron, while the beige at the bottom represents the interior. Within the neuron are large proteins covered in negative charges. These large proteins are unable to cross the membrane, and thus they serve as a permanent reservoir of negative charge. Within the membrane are several channels, and we'll start with the sodium-potassium pump. Adenosine triphosphate, ATP, first binds to the pump. This is broken down into adenosine diphosphate and a free phosphate that briefly remains attached to the pump. This reaction liberates some energy, and this energy is used to pump sodium out of the cell. Next, the phosphate is released from the pump. This liberates enough energy to move 2 potassium ions into the cell. So each molecule of ATP used results in 3 positive charges moving out of the cell and 2 moving in. The interior of the cell is becoming more negative. Now, if you've been paying attention, you might be questioning what I just said. The inside of the cell obviously contains more positive charge than it does negative charge, so in an absolute sense, surely the inside of the cell is positive. And it absolutely is. The negative sign on the inside of that membrane is just letting us know that the inside of the cell is less positive than the outside. Now let's take a look at that graph in the upper right corner. The sodium-potassium pump has established a charge differential across the membrane. It's referred to as a potential because it has the potential to do work. It's also called a voltage. For a cell that's at rest, this resting potential is minus 70 millivolts. The negative sign indicates that the interior of the cell is less positive than the exterior. Positive charges will attempt to move into the cell if the opportunity presented itself. If we were to have a positive value for our voltage, this would indicate that the interior of the cell was more positive than the exterior. And if we had a value of 0, well, that would mean, of course, that the charge was exactly the same inside and out. There wouldn't be any potential, and thus no voltage. Sodium-potassium pumps set up and maintain a very unstable gradient. That's the resting potential. It takes a lot of energy to maintain this unstable situation. In fact, about 50% of the energy used by your brain is used just by these pumps. But now that investment is about to pay off. Mechanically gated channels and ligand-gated channels are found in the dendrites and cell bodies of neurons. Gated channels can be opened or closed. When opened, they allow ions to move passively down their concentration gradient. The example I'm going to use here is of a ligand-gated sodium channel. A ligand is a signaling molecule that binds to something else, usually a channel or receptor. The channel in our example binds to a specific neurotransmitter, shown as a red square here. The neurotransmitter is the ligand. Provided the ligand is the correct shape, it will cause the sodium-gated channel to open. This allows sodium to enter the cell. The sodium will be dispersed within the neuron, and if enough of it makes it to the axon hillock, don't worry, we'll come back to that, it might cause the generation of an action potential in the axon. On our graph, we can see that the influx of sodium is decreasing the charge differential across the membrane. The interior is becoming more positive. If we reach a value of negative 55 millivolts, something exciting happens. An action potential is generated. Voltage-gated sodium channels are found within the axon hillock and axon of the neuron. They are closed at resting potential, but when the membrane potential reaches minus 55 millivolts, these channels will open, and this allows a flood of sodium to enter the cell. The flow of positive ions into the cell is known as a depolarization. It began with the opening of the ligand-gated sodium channels and continued with the opening of the voltage-gated sodium channels. So much sodium enters that the polarity of the membrane actually flips, and the interior of the cell becomes more positive than the exterior. By the time the channels have closed completely, the potential on our graph has reached positive 30 millivolts. As this is occurring, the neurotransmitter will detach from the ligand-gated channels and those channels will close. Because voltage-gated channels are only opened within a certain range of membrane potential, the voltage-gated sodium channels will close as well. The massive depolarization of the cell triggers voltage-gated potassium channels. They open, and because there are lots of these channels, potassium rapidly leaves the cell. This causes a very quick repolarization of the membrane. The polarity of the membrane flips back again as the interior of the cell becomes less positive than the exterior. The switch in polarity causes the voltage-gated potassium channels to close. Because the voltage-gated potassium channels are numerous, and they can't close instantaneously, the membrane potential undershoots the resting potential. This is known as a hyperpolarization. The sodium-potassium pump will now restore the resting potential. Sodium is once again pumped out, and potassium is pumped in. This will take a little while, and by that I mean a tiny fraction of a second, but it will ultimately return the membrane to a potential of minus 70 millivolts. Note that the pump never completely quits, but its actions are overwhelmed by the much quicker actions of the other channels during an action potential. Now let's put this all together and look at how an action potential is propagated along the length of a typical neuron. The ligand-gated channels that we discussed earlier are found on the dendrites and the cell body, where other neurons synapse with our cell. Ligand-gated channels are not found along the axon, well, at least not for this example. The cell has several dendrites, and let's assume that ligand-gated channels on only some of these dendrites have been activated. When these channels open, they allow sodium ions to enter the cell. These ions diffuse through the cell body to the base of the axon hillock. Because these ions need to diffuse and disperse themselves across the entire cell, it takes a rather large influx to bring the hillock up to the threshold of minus 55 millivolts. If sufficient sodium moves to the hillock and brings us up to our threshold, voltage-gated sodium channels will then open, initiating an action potential. An all-or-nothing signal travels the length of the axon. The magnitude of this signal remains constant from the hillock where it starts to the axon terminal where it ends. At the terminal, this signal may cause the release of neurotransmitters that will initiate a new signal in another neuron or muscle cell. We'll examine how this signal is propagated, starting with how this occurs in a naked stretch of axon, like what we see here with the axon hillock. We'll follow this by how propagation occurs in myelinated segments. Here we have a segment of non-myelinated axon, naked axon. Notice how the same channels we discussed before are repeated over and over again. Let's divide this into segments. All of these segments of membrane began at resting potential, and these segments are tiny, they're microscopic. The first segment is the axon hillock. Sodium ions flowing in from ligand-gated channels in the dendrites and cell body bring the membrane to its threshold voltage. This causes voltage-gated sodium channels to open, causing the area to fully depolarize. Note that much of this sodium diffuses down the axon towards the right. Now, several things are about to happen simultaneously. In segment 1, the sodium voltage-gated channels will close and the voltage-gated potassium channels will open. In segment 2, the influx of sodium will immediately bring this segment past threshold and the voltage-gated sodium channels will open. Are you ready? Here we go. Note that segment 1 has repolarized, while segment 2 has depolarized. The pattern is repeated. The influx of sodium through segment 2 has activated voltage-gated sodium channels in segment 3. Voltage-gated potassium channels in segment 2 caused it to repolarize. Back in segment 1, potassium channels have closed and the sodium-potassium pump is now working to bring the hillock back to resting potential. Now, for those of you paying close attention, you might be asking why I've only shown the movement of sodium ions to the right in the diagram. Surely some of these ions must also diffuse towards the left. Well, you're absolutely right. Sodium ions will flow in both directions. I haven't shown this because the ions moving to the left will not bring about an action potential. Sodium ions entering segment 2 will have no effect if they diffuse into segment 1, because segment 1 is rapidly losing positive charge at the same time through its potassium channels. This means that the action potential can only travel in one direction, away from the axon hillock that initiated it. These cycles are repeated over and over again. Note that when the sodium and potassium voltage-gated channels are doing their thing, the segment is said to be in its absolute refractory period. It cannot initiate a new action potential. When hyperpolarized, the segment is said to be in its relative refractory period. It could fire, but it's unlikely because it would require a very large influx of sodium to bring it up to threshold. After the wave of action potentials moves through, each segment will once again return to resting potential, making the segments once again receptive to new action potentials. So what happens in a myelinated axon? A myelinated sheath consists of several layers of phospholipid membrane. These are laid down by Schwann cells in the peripheral nervous system or oligodendrocytes in the central nervous system. The myelinated sheath acts a little bit like the insulation on a copper wire. Please note that my drawing is not to scale. In fact, I hope it's obvious that nothing in this video is to scale. The sheath would be considerably longer, if to scale, because each of those segments is a whopping 1 millimeter in length in the peripheral nervous system. The myelin prevents the movement of ions in and out of the axon. Therefore, this covered portion of the axon is unable to generate new action potentials. Between the myelinated sections are nodes made up of naked axon. These naked sections have the pumps and channels we know and love and have access to interstitial fluid. These areas are able to generate action potentials. The node to the left of the myelinated sheath will receive sodium ions from the preceding section, just as we've seen before. Once again, this will cause the cell to depolarize as voltage-gated sodium channels are opened. But here's the new part. The sodium that enters will diffuse across the cytoplasm of the entire myelinated portion of the axon. Diffusion occurs very quickly. This is referred to as saltatory conduction. Saltare means to jump in Latin. The action potential appears to jump from node to node. When sodium reaches the next node, it causes voltage-gated sodium channels to open and initiate a brand new action potential. The conduction of signals within the nodes is identical to what we have already discussed. What makes this system special is that the action potential is regenerated only in the nodes. There are limitations to how long each myelinated stretch can be. The longer the sheath, the more the ions are diluted before they reach the end. If the distance is too great, threshold will not be reached in the next node. But so long as thresholds are met, the signal will be transmitted the entire length of the axon without a decrease in magnitude. Myelinated neurons not only conduct signals great distances, over a meter in many cases, but they also conduct signals 10 to 15 times faster than naked axons. Ha! I did it in under 15 minutes. Looks like you'll be buying your own pizza. If this was helpful to you and you'd like to see more of these shorter videos, please let me know. Leave me a comment, like and subscribe, share it with your friends, insomniacs that you know, whatever. All that cool social media stuff that I have no interest in. And cheers.